So up until now, we have looked at various control volumes and different effects of compressibility versus incompressibility, steady flow versus unsteady flow, uniform flow versus non-uniform flow. But in each of those cases, we were looking at a steady control volume or a stationary control volume that we put into a pipe, or I don't remember what our other examples were. But now we want to look at a moving control volume. And the motivation behind that is as follows. Let's say that we have an airplane that's flying through the air, and we want to analyze the mass and fuel flow rates into that engine. So to be more explicit, let me draw the engine here. Looks something like this, let's say. And we know that, at least from the perspective of the airplane, that there is air coming into the engine. That is, air gets sucked into the engine. Air gets blown out of the engine at some speed. And then we have some fuel. Oops, fuel. Spell that right there. Fuel going into the engine. So we have air coming in the inlet, fuel being pumped into the engine, and at the outlet we have air plus the combusted fuel as well. And we'll give it here in just a second. We'll give the conditions on all of these flows, and the object is going to be, given what we know about the air coming in and the mixture coming out, how much fuel are we adding to the are we pumping into the engine? Now, if you consider an airplane flying through the air, or if we consider this engine that's, whoops, let me do this in red here. This engine moving through the air, it's pretty clear that if we had some stationary control volume with the engine moving through it, right? At some point the engine is here, and at some time later the engine is here, and at some time later the engine is here. All of a sudden the problem becomes really difficult, because we don't know, well, do we analyze the system when the engine is in the middle? And if we do analyze the system when the engine is in the middle, do we have to take anything else into account? How are we going to deal with the fact that the engine itself isn't stationary? And the answer is as follows. The answer is we don't do this. The answer is that we create a moving control volume that conforms to the engine itself, which I'll draw up above here. So now the control volume and the engine are moving along together, and so we have a different question, which is now how do we deal with the fact that the perceived inlet flow or the perceived outlet flow or even the perceived fuel flow are different whether you're moving along with the flow or not. And to deal with that, we have to rewrite the Reynolds transport theorem to deal with relative velocities. So before we had the Reynolds transport theorem was d dt of our control volume, the integral over our control volume of rho b dv plus the integral over the control surface of rho b v dot n hat dA was all equal to the change of capital B, whatever extensive property we're looking for the particular system. Now, if we look at a moving control volume, I'll go back to red here. Let's say that our control volume is moving, in this case I'll draw it to the right, doesn't really matter, at some velocity, and we'll call it v sub cv. That is, it's the velocity of the control volume. Then any any fluid particle that is moving with respect to this control volume, in particular that's moving across, let's say, across some boundary, well, we call that velocity vector v, as we have before. But we know that we can write v, the absolute velocity, is equal to the velocity of the control volume plus what we'll call w, which is the relative velocity of the fluid with respect to the control volume. This is exactly what you did in your dynamics class when you were dealing with translating or rotating systems. And we can rearrange this to show that the relative velocity, of course, is equal to the absolute velocity minus the velocity of the control volume. Now here's the nice part. The nice part is that when you